Okay, this diagram is from the patent, and it's a propulsion device, but that may seem strange because there's no propellant, and there are no moving parts, so that's sort of interesting. Um, these side pieces are actually supposed to be attached here by these lines, well, here and there. It starts here at the with the ferromagnetic core. It's right here. It's in a loop. It's actually a ferrite, which is non-conductive. It goes all the way around. And then there's 4 coils here, and these coils will magnetize the ferrite. Then in the center here, this is a metal plate of a parallel plate capacitor with one plate on this side, and the other plate is hidden behind the ferrite underneath. And the ferrite then acts as a dielectric between the 2 plates. And you have the same thing below, another plate, and that plate on the other side there too. Now these 2 side pieces, they have a capacitor too, parallel plate capacitor, with one plate being on this side, and inside there's a plate here you can't see, but you can see it on this one over here. And it's separated by a regular dielectric, it could be a plastic or something, but something that's similar to the same dielectric constant that the ferrite has here. And so that's the basic components of the device. That's all there is to it. This little extra coil here can be used to give feedback. It has to do with how this thing is driven. There'll be a current alternating back and forth through this, so that the magnetic field created by this ferrite is reversing back and forth. But see, the whole idea is that this device will actually propel itself in a direction without equal and opposite reaction. And so it seems like momentum is not being conserved. So in order to understand this device, we have to really look at the basic situation with conservation of momentum to see how this is even possible. So let's go ahead and go back to the basics here. Now we're talking about conservation of momentum, and how that works is, for example, let's say you have 2 blocks here and a spring between them. And we can imagine that these blocks are on a frictionless surface, or they're in space or something. And the law of conservation of momentum says that the momentum of the whole system never changes, even though part of the system could have a momentum that changes. The whole system momentum always remains the same. So for example, right now we have a situation where the momentum is 0. Okay, so we release these. Both of the blocks have a momentum, but if you sum up their momentum, it still is actually equal to 0. So the momentum didn't change. But, why didn't the momentum change? I mean, is it something like, is that the law that's really being obeyed here? If you think about it, the conservation of momentum in this case was actually the result of something else. And that is the law of equal and opposite reaction. In other words, it wasn't like momentum was magically conserved. It's because the force here from the spring was equal and opposite with each block. And so this essentially caused the momentum to be conserved. And so it's not like, so you could say that the equal and opposite reaction is a more basic law, which the conservation of momentum is just a result of that law. So the equal and opposite reaction pushes the blocks apart, and that ends up conserving momentum. So instead of looking at momentum itself, let's look at this equal and opposite law. Now, when that law was first established back in the times of Newton, it was before they understood atomic structure, and so, they talk about the spring being in contact with these blocks in order to apply a force to them, right? But the situation is that the blocks are actually made up of atoms, and the spring is made up of atoms. What does it really mean to be in contact with those blocks? I mean, it's not like the electrons are touching the electrons or the protons are touching the protons. What it really means, what's really happening is that if you get to the very basic forces, it has to do with a kind of electrostatic repulsion that gives you the feeling of contact, or that causes contact to happen. So let's look at the law of equal and opposite reaction in its most basic form. In order to do that, what we want to do is let's look at some basic charged particles. I'll give us a good example of that. Let's say you have a positive charge here, and that charge is next to another charge. And we know these will fly off just like those blocks did, because they're both positively charged, so they'll fly off just like the blocks did. And it'll be with equal and opposite reaction, and then, of course, momentum will be conserved. But when you're looking at the atomic level, it's interesting because the equal and opposite reaction is actually a four-step process. For example, the first step is we can start with this charge here, and the first step is this charge creates an electric field. And now I'm showing the electric field here with little pointers for the direction of the field. And instead of showing length like with vectors, I'm showing it by the strength of the field. I'm showing it by the opacity. So that's why it gets more transparent as it goes out, because the electric field gets weaker. But this is the direction of the electric field for a positive charge. Now that's the first step. It creates a field. Now the second step is this charge is inside the field, so it feels a force because it's in the electric field. So that's the second step. Now the third step is this charge also creates an electric field. And now the fourth step is this charge is in the electric field of that charge, and so it experiences a force in the opposite direction. So of course that force ends up being equal and opposite, and then you end up considering momentum again. But notice it was a four-step process. So let's consider an idea here. Let's say, for example, we go back to this charge, and we say, okay, let's remove this charge from the picture. But let's say miraculously the electric field that it created remains in place. Okay, so now let's go through our process again. Okay, we've got the electric field. This charge is an electric field, so it feels a force away from where the charge used to be. So now this charge is creating an electric field. But notice we don't have a charge here for there to be a reaction to the force. So what happened in this case, there's no equal and opposite reaction. So if you have an electric field that's not being caused by a charge, and you have a charge in that electric field, then Newton's third law of equal and opposite reaction will not apply. Now, of course, you're saying, well, I cheated because I took the charge away, but I let the electric field stay there, which obviously wouldn't be possible. However, it turns out that you actually can create an electric field without a source of a charge at its source. And you can do that by changing a magnetic field. So we should create that type of electric field from a changing magnetic field, and then we should put a charge in that field. We'd have the same situation like this, where there was not equal and opposite reaction. So let's look at a little more practical approach here. So we want to create an electric field by a changing magnetic field, so that doesn't have a charge at its source. So we can do that. Let's start with a ferrite block here, shown here, and then this is looking at the same block end on. And basically, we're interested in the area in the center here. But let's say, okay, first we want to create a magnetic field, right? Okay, so let's create a magnetic field. We'll put a couple coils on here. I'm leaving this middle part open for a reason. So these are connected in series. So we can just run some current through here, and then we can create a magnetic field. Now, of course, a constant magnetic field isn't going to create an electric field. It has to be changing. Now, we can't really have a constant electric field from this situation, because you have to keep changing the magnetic field continuously, and you'd end up with an infinite magnetic field. So the only thing we can do is we can alternate it back and forth, and we'll create an electric field, but the electric field, of course, will have to be alternating back and forth also. So let's do that. Let's reverse the current back and forth. So now we're going back and forth, changing the direction of the current, and the magnetic field reverses as the current reverses. And notice that the magnetic field is strongest when the current is at its maximum. So now, since this is a changing magnetic field, it creates an electric field. Now I'm showing the electric field with the little green pointers again. And now there's actually an electric field all the way around here, but I'm just showing it in this central area because that's what we're interested in. But we have an electric field. Now this electric field there that is being created by the changing magnetic field. Now notice that this electric field is actually at its maximum at the greatest change in the magnetic field, which turns out to be at the same point where the current in the coil stops. So this electric field that is being induced by the changing magnetic field is at its maximum when the current stops as it goes back and forth. Now, if you look at this picture, you can see that looking down the end of it, you can see that the electric field actually goes around the ferrite, and it goes back to, and it doesn't go back to any source. There's no positive, there's no charge here, positive or negative, that's creating this electric field. So this is the kind of electric field we were talking about before that has no charge as its source. Now I'm showing it by the strength of the field by the opacity again. As you can see, these get dimmer here. But notice it's reversing. Notice that it's going the opposite direction on this side of the ferrite as that ferrite, because it's basically circling around it. Now to simplify this a little bit, let's take the magnetic field lines out. Now what we could do here, of course, is we could add another coil. We can add another coil to the center, a kind of secondary coil. And as you can see over here, you'll notice that as the electric field is reversing, it is actually pushing the electrons or the charge through the coil, around the coil here. And so you could actually induce a current in this coil. And that's how a transformer works. So for example, we've just shown how a transformer works. And the reason I'm bringing this up is because I'm not talking about something new or strange. This is, there's a million transformers working constantly right now all around the world. And it uses a very simple principle. So it's not something new or strange. This actually happens every day. But let's do a trick here. Instead of the coil, let's get rid of the coil. And let's try to get some charge into this problem, because like we put the charge in the electric field before, we want to put some charge in this field. Now, to get charged in there in a practical way, we'll use a capacitor. So we'll put a capacitor here. And what I'll do is I'll put the plates so that the plates straddle the ferrite. And since the ferrite's non-conductive, we can have a capacitor here. And I'll have the green part means that the plate is positively charged, and the red plate means that it's negatively charged. So what I've done is I've charged up the capacitor to just be charged up so that one plate's positive, one plate's negative. But notice they're on the other side of the ferrite here. And notice that as the electric field changes, it'll apply a force to that charge, because that charge is now a charge that's in the electric field. And notice on this side that the negative charge will go the opposite direction of the electric field pointers on this side. So they actually will experience a force in the same direction at the same time. Now this parallel plate capacitor, these plates are attached rigidly to the ferrite. So the force it feels will be on the entire thing. So what kind of force did you see in this situation? So you see this kind of force. The force is going back and forth because as you can see, this is a positive plate here. So as the electric field changes direction, the force on this plate changes direction back and forth. And the interesting thing is that since this is negative, but this electric field on this side is actually the opposite direction as that side, so the force ends up being in the same direction. So this is what's going on there. The forces are alternating back. This is an actual force, though, on the plates and the ferrite. Now, what's interesting about this force is that there is no equal and opposite reaction, because the electric field generated by the capacitor has no charge with which to interact, because this electric field didn't come from a charge. It came from a changing magnetic field. Now, of course, we're not getting too far here because it's the force is just going back and forth. So let's do a trick. Let's set it up so that we reverse the charge on the plates. And we time it so that it changes at the same time that the electric field changes, the induced electric field. So if you look at this, in fact, what we could do is we could actually have the capacitor hooked up to this coil that's supplying the magnetic field. And so that when this current stops, the plate is charged to its maximum for each direction. So notice that so when the current is stopped, not only is the induced electric field at maximum, but the charge is maximum on the plate. But it's reversing direction at the same frequency as the alternating induced electric field. So in this situation, your force would be like this. Now look carefully. You'll notice that when it goes to zero, both the plates are uncharged and the electric field that's induced is zero. But then when it gets to that point, the charge reverses and the on the plate reverses, and the electric field that's induced also reverses, so that ends up that each force is always in the same direction. So that is exactly how the inductive drive works. And it's propelling itself in one direction without reaction. Now let's go back to the diagram again. So in this diagram, you look up here, the part that's highlighted in red, and you can see that that's exactly what we just looked at. We just figured out how this piece of the device works. Because you have your coils, you have your parallel plate capacitor in the center. But now in this particular case, we also have another copy of it down below, which is exactly the same thing as up here. So you have two of them actually. And what I did here was I connect the ferrite together so that you have so you can create a magnetic circuit, which is useful for like in transformers. And you have to, of course, charge up the plates in the right way so that it works out right. And so what this will do is create a force in a single direction. It could actually be the other way, depending on how you have it hooked up. So what we've done is we have these coils hooked up in series, and they're actually connected to these capacitors in the center. And so as we alternate the current back and forth, we get the same situation where we described, and we'll get a force in a single direction. Now, there is a little detail here that I didn't talk about because I didn't want to overcomplicate the issue. But it turns out that on these edges, there is actually a magnetic field created from the changing electric field in the capacitor. And that magnetic field goes along the length here of this. But because there is a surface current going up and down along that edge caused by the magnetization of the ferrite, it actually creates another force. This force is actually in the opposite direction. Now, ironically, this force is also non-reactive. And it's actually not the same amount as this main force. In this geometry, it's about half. If you count all four of the edges, it's about half of this force. But it is detrimental because we don't want to, we want to get the force in one direction. So that is the purpose of these two incapacitors. Because what they do is they also are having a changing electric field inside them, which also creates a magnetic field. But if the magnetic field is going this direction on this one, the magnetic field on this one is going this direction. So when you attach these pieces to each end, it eliminates that magnetic field, and so it gets rid of this little reverse force. And so because of that, you end up with a force in one direction, just like described earlier. So that is exactly how the inductive drive works. Now, as far as the actual equations, the equations have been done to show exactly how much force this is, and everything has been worked out. And you can actually, if you want to get the if you want to get the actual quantities, you can get this book here. This book is called Alien Technology, and you can get it from Amazon.com. This book gives the equations for the inductive drive and a number of different variations of it, actually. It also discusses the energy usage of it and some further applications. So it's very useful. And the idea that momentum is not conserved is actually very fundamental. And to discuss that, in more detail, you can also get this book here called The Electromagnetic Universe, and this discusses how, in general, conservation of momentum can break down, and it's very detailed. And so, with these two books, you should have all the information you need. Now, as far as some of the technical details of this device, is that it's not a real strong force. I mean, it's strong enough that given proper resources, you should be able to get a measurable effect without too much difficulty. But the engineering required to get it to lift its own weight will actually be quite a challenge. But I think the advantage of such a device is great enough that a concentrated effort would actually be advised. And so that's it.